Hi there, welcome to my talk on generators, coroutines, and nanoservices. My name is Reuven Lerner. I'm really delighted to be joining you here at PiterPy 2020. Anyway, a few words about myself. I am a full-time Python trainer. I have my own business. I've had it since 1995. Most of the time, before the coronavirus and COVID-19, I was flying around the world teaching Python at companies all over. Last year, I was in the US, the UK, Europe, Israel, where I live, India, and China. This year, I'm still teaching companies all over the world, but of course, on WebEx and Zoom. I also have a whole bunch of courses that are not for corporations, but are for individuals and small groups, including weekly Python exercise, which is a way of improving your Python skills through, well, a weekly Python exercise. I also have a book that just came out, Python Workout, published by Manning, which includes exercises to improve your Python skills and improve your fluency. And I have a free weekly newsletter that I put out called Better Developers that's currently read by about 18,000 or 19,000 developers around the world. But let's talk about generators and coroutines. And let's start off by pointing out this is not a talk about async I/O. It is true that async I/O, which is a modern, new way of doing concurrency in your Python programming, uses the term coroutines quite a lot. And there is some overlap between the coroutines that we're going to be talking about here and the coroutines in async I/O. And I'll mention that a little bit at the end of this talk. But overall, this is not about async I/O. This is about a distinct set of technologies and a distinct way of thinking about how we're going to write our programs and how we can structure them. So let's start off with what I call the dumbest function in the world. So we have here def myfunc, return 1, return 2, return 3. And I then want to run myfunc and print the result from it. So the question is, what happens when we run this code? And you are hopefully not surprised to discover that it prints out 1, right? Well, why would that be the case? Because, well, return in a function means stop the function right now and return a value. And here we're going to return 1. PyLint even warns us, hey, those final 2 lines are unreachable. You're not going to be able to get to them. There's no if there. It's always going to return 1 and then return 2 and then return 3. And even Python's byte compiler, which traditionally does not do a lot of sophisticated analysis of the code, it just takes our code, turns into bytecodes, it also ignores the final 2 lines. In fact, we can take a look at that if we use the dis module from the standard library. It includes the dis function. So it's dis.dis. If we run that on our function on myfunc, we will see these are the bytecodes that Python produces, the compiler produces from our function. So first we're going to load the constant 1, and then we're going to return that value. End of story, game over. Well, let's look at a slightly different function. Def mygen, so it's got a different name, and then we're going to do yield 1, yield 2, and yield 3. All right, so the big difference here is instead of saying return, we're saying yield instead. Now, yield is a keyword in Python, it is a distinct keyword. But what does it mean? What does it do? Well, once again, I'm going to run my function and I'm going to print the result. But this time, I'm not going to get 1, 2, or 3. This time, I'm going to get generator object mygen at blah, 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 blah. What's going on here? What was the difference? Well, the difference is the use of the yield keyword. When Python compiles our function, it notices yield and immediately says, aha, this is not a regular function. This is a generator function, which means that when you run the function, you are not going to get back a result right away. It's not going to run the body of the function. Rather, you're going to get back a generator object. And a generator object is one that implements the iterator protocol. We'll talk about that in just a moment. But running a regular function gives you a result. Running a generator function gives you a generator. Well, how does Python know? Well, once again, it notices the yield, and at compilation time, it sets a flag in the CO flags field actually inside of the code object. And you can see here if we use dis.showCode on mygen, on our generator function, then it marks it as a generator. I should also mention, by the way, that for many people in the Python world, there is no difference between a generator and a generator function. people use the term generator to describe generator functions. Technically speaking, that's not the case. A generator is the thing that we get back from running a generator function. But as you can see in show code and in many, many other things that people have written and said, let's face it, everyone just calls them generators. Well, what if we then disassemble our generator? You can see that the same lines, just with yield instead of return, well, yields a totally different set of bytecodes. We're going to load the constant 1, yield it, and pop the top. Load the constant 2, yield the value, and pop the top. Load the constant 3, yield the value, pop the top, and then we load none and return that. This means several things. This means that yield is baked into Python because it is one of the bytecodes. It's one of the lowest level things that exists in the language. And it also means that we are going to get results back from each of these. We're going to get 1, then 2, then 3, and we'll see that in just a moment. But before we can talk about that, what is a generator? Well, as I said before, a generator is an object that implements Python's iterator protocol. And you can create your own objects that implement the protocol, but generator is a specific object that implements that protocol in a nice, tight, compact way. So the protocol is 3 very basic things. You run iter on an object and you get its iterator. In the case of a generator, it is its own iterator. So when Python says, hey, who is your iterator? Or are you iterable? And if so, who's your iterator? Then the generator says, me, I'm my own iterator. Then what we can do is we can say, give me the next value, and we get the next one with next. And next will then either give us the next value or it will raise the stop iteration exception. So that is all that is in the iterator protocol in Python. You can ask something for its iterator, you run next on that iterator, and when it gets to the end, it raises stop iteration. And it was purposely designed to be really simple so as to encourage us to add the iterator protocol to as many different objects as possible. So given this, how does a for loop work? Well, everyone, like from the first day or two that they start programming Python, sees how for loops work. We say for one item in our string ABCD, print one item. So what's happening is exactly what I just described from the protocol. First of all, Python asks, is this string iterable? The answer is yes. So it says, okay, if you're iterable, give me your iterator. So it gets that back. And then it says, okay, iterator, give me the next thing and the next thing and the next thing. And this is why Python for loops don't need to have indexes, unlike, say, C, where we go from 0 until some index. Here, no indexes are around. It's up to the object, it's up to the string to decide when we are done and what we should be getting along the way. So we're going to get the next and the next and the next. And when we get to the end, then we get stop iteration. So we get the first thing, then the second thing, third thing, fourth thing, A, B, C, D. The for loop then traps the stop iteration exception, stops the loop, and continues with the rest of the program. Well, what if instead of doing that with a string, A, B, C, D, we were to do it with our generator, for one item in mygen, print one item? Well, exactly the same thing will happen. We're going to ask, is it iterable? And we just said before, generators implement the iterator protocol. So yeah, the result of running a generator function, a generator, is indeed iterable. Who is its iterator? It's its own iterator. So then the for loop says, okay, iterator, generator, give me your next thing, your next thing, your next thing. Each one is assigned to one item. And then we get 1, 2, 3, 1, 2, and 3, and then stop iteration, which exits the loop. What if I want to do this manually? What if I don't want the for loop to do it for me? Well, I can say g equals mygen. I've now created a generator object. And we can compare here. We can say, hey, what's g? And we will get the printed representation, the repr of this object. And we'll even see what address it's at. Now, I personally think it's kind of weird that we get these addresses, memory addresses in Python. Yes, it's true that the ID of an object is the same as its address. But even so, do I really care about the address? I can't get to it in any event. So we see that g is there, but we also see that iterg has exactly the same value, which means that the generator is indeed its own iterator. They're running the built-in iter function on g will just return g again. Well, what about next? So here, just sort of for the sake of remembering and understanding, this is our generator's definition. Then we say g equals mygen. So if I then say next on g, what will happen? It's going to run up to and including the next yield. Run next again, up to and including the next yield. We get 2 back. Next g, up to including the next yield. Next g, stop iteration. So each time we run next on our generator, it's going to run, as I said, up to including the next yield, at which point it goes to sleep. It stops running. We have our value. And when we then run next on it again, it picks up from where it left off from. So next tells a generator, as I just said, to run through the next yield statement. And this can be a lot of code or a little bit of code. We can have 100 lines, 1,000 lines, 1,000 iterations of a loop, because you can have next inside of a loop. or it can be one line. Typically, not always, but typically you'll have one call to yield from within a generator function, and then you'll just have it loop and loop and loop. But you don't have to. You can have as many yields as you want. And the function state, the local variables inside the function, stick around between the iterations, across those iterations. So you don't need to worry about, well, wait a second, local variables, right? Local variables do go out of scope and then are sort of destroyed when a function returns. But the function here is not returning. The function is yielding, going to sleep, waiting for the next. Let's look at some examples of generators. Here is perhaps the most famous example, fib, for the Fibonacci sequence. Now, one of the nice things about a generator is it can describe an infinitely long sequence, but it doesn't have to take an infinitely long amount of time to run. So we say def fib, and what is the Fibonacci sequence? It starts at 0, then 1, and then the next number is the sum of the previous two. So I'm going to start with first and second. I'm going to yield first, and then I'm going to do this little switcheroo using tuple unpacking. I'm going to say first comma second equals second comma first plus second. So what was previously the second is going to become the first, and the first plus second is going to become the second. So we're constantly moving things to the left. Now, obviously, this is an infinitely long series. So in theory, we could get an infinitely large number of values back. However, because with each yield, it goes to sleep, and it waits, and it waits, and it waits, so we can get it step by step by step, and we don't have to worry about trying to fill our data with an infinite amount of numbers. So I'm going to create the generator here, g equals fib, and then we get next, and next, and next, and we can keep going next as many times as we want until we'll run out of memory. Now, you should not do this. You should not run list on fib, because what's going to happen? Well, list will just collect data until you get stop iteration, try to create a list from it. But of course, that'll never happen. So you should not do that unless it's to your friends or colleagues' computer when they go out to make a cup of coffee, in which case you did not hear it from me. Okay, another example of generators, readn. So if I want to iterate over a file or a file-like object in Python, I can do that. File-like objects are iterable, and I will get, with each iteration, all of the values up to and including the next \n, the next new line character. So that's great if I want to read a file line by line by line. But what if I don't want to read it line by line? What if I want to read it chunk by chunk? What if I want to read it 3 lines at a time or 5 lines at a time? So what I'm going to do is I'm going to open the file and then have a while true loop. And inside that while true loop, I'm going to have a list comprehension that's going to call readline, f.readline, which calls the next line. So I'm going to do that how many times? N times. So if n is 5, I'm going to get 5 lines. I'm going to join them together. But wait, f.readline returns an empty string if I'm already at the end of the file. So I'm going to call f.readline 5 times, let's say. But 0 might be blank. 0 of them might be blank. I might get lines for all of them. Or they all might be blank if I'm already at the end of the file. And if I'm already at the end of the file, then join them together will give me still an empty string. So if output, if it is a non-empty string, then we'll yield it. We're going to give the person the last thing. Otherwise, we're going to break. And if we break, then we go to the end of the function, and very good. Next example, next vowel. I can give it a file name here. I can say, let's open this file and go through it one line at a time. Then let's go through each character in the line. Then let's check, is the character a vowel? And if so, we're going to yield it. So we will get, in order, one at a time, each of the vowels in this file. Again, how long of a sequence are we going to get? We don't know in advance. How big is the file? We don't know in advance. Could this be a 10 terabyte file? Yes. But because we're reading through it one line at a time and giving one vowel at a time, it doesn't really matter. So we're able to deal with much larger pieces of data, much larger files and resources than we otherwise could do it. So when do we use generators? So if we have a potentially large or infinite set of values, often it's easier to express the idea as a function, right? There are things that just don't work as well as objects. But if I have a function, I can describe it really well, like it did with Fibonacci there. Often I have to set things up. So I have to set up a network connection. I have to set up a file. I have to connect to a database. And I then want to use the fact that my function's scope, or my function's local variables don't go out of scope. And I can cache that information or use that. And thus, maybe even if the first call will take a while, the subsequent calls won't take so long. Well, what about this? Now let's look at something a little different and weird. Here we have def mygen, x equals none, so far so good, while true, and now we see this, x equals yield x. Well, until now, yield has always been a statement that returned a value to us. But now it's not only going to return a value, it's also an expression. It has a value that can be assigned to a variable. And then we say x times equals 5. But what does that mean? How does that work? Well, if yield is an expression, the same rules for generators still apply. Each call to next runs the generator through the next yield. And after yield, it goes to sleep. But, and this is the important thing, the yield is on the right side of an assignment expression or assignment statement. That means that the assignment can only happen when we get a value back from yield. Where is yield going to get a value back from? Well, we can inject a value from outside. Yield can now receive a message from the outside world. That received value will replace yield, put it into assignment, and then it will continue. So with each next, we will get a value back, but we can also provide a value, get a value, provide a value. And so we could use next to advance our generator to the next value. But we're going to send a value using the send method, the special send method. And we can actually send any Python data structure we want. So here in this example, g.send of 1, 2, 3, we're sending an integer. But I can send a string, a list, a tuple, a dictionary, a function, a module, whatever you want. If you want to say g.send instead of next, you can do that with g.send of none. There's no difference between doing the two there. So if I now do this, let's go back to our generator for a moment. And so I'm going to say g equals mygen. That's going to give me a generator. And then I'm going to say g next of g. I need to do this first. I need to first get a value back from the yield so to prime it as it's known. So then the next time I give it a value, it'll be on the right side of that assignment. So now I can say g.send of 10. What happens? Well, yield x is replaced by 10. So it's now x equals 10. Then x times equals 5, that makes 50. We come back around the top of the while loop, we yield x, we get 50 back, and now it's once again gone to sleep on the right side of that assignment. If I say g.send of 23, what's going to happen? Well, yield of x is replaced by 23, x equals 23, x times equals 5, that becomes 115, we get that back, 115. What if I say g.send of abc? Well, yield of x is replaced by abc, the string, x is abc now. X times equals 5 is going to be ABC, 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 5 times. That's what we get back. I can also say g.send of the list, 1, 2, 3, and then we get 1, 2, 3, 5 times. It's too long to print there, too long for me to say, but you understand what's going on. We're able to basically provide data and then get something back. It's like a little calculating machine there. It's like calling a subroutine. And indeed, these are known as coroutines. Coroutines are implemented in Python as generators. And a coroutine waits to get input from elsewhere. We're going to use send to give it a value. And that data is received with yield as an expression, typically on the right side of an assignment, as we've seen. And then we're going to go around and around and around, giving it values, giving it values, giving it values, and we'll get a value back for each one. The local state remains across calls. And so the difference between a regular function call and a coroutine is that a regular function call, if I were to do it, it would have to build up whatever state the coroutine already has. And that's part of the savings that's involved and the efficiency involved in the coroutine. I should add, this means the coroutine is in memory all the time. Its local variables are there and it's taking up space. But that sort of time versus space trade-off is one that we often make. And here it's better to have it in memory because it's not really going to take up that much memory versus having to do all of our startup costs. Now, as of Python 3.8, we have a new operator, the assignment expression operator. No one calls it the assignment expression. It's the walrus operator. Why? Because if you turn your head this way, it looks sort of like a walrus. Very, very controversial in the Python world. Oh boy, look at what people wrote and said about the walrus operator back then. But in this sort of circumstance, it actually can be really useful because what we can do is say, while x walrus equal yield of x, which means we're going to get a value from the user who sent it to us with send. And if that is an empty value, meaning in a Boolean context it's going to be false, meaning that we're going to get none, 0, or something empty, then the while will be false and we'll break out the while loop. But if we got a value that's not false in a Boolean context, it'll be assigned to x, then we'll do x times equals 5, and we'll yield again. Notice that the yield here has to be in parentheses, otherwise things don't quite work right. So what if you don't want to prime it? Because it's kind of annoying that each time you have to say next, just to start up your generator. So David Beasley gave a great talk in 2009 all about all about generators and coroutines. And he suggested using a decorator to do this. And the decorator runs next and then returns the coroutine, returns the generator after it's already been primed. And then you can just use send on it right away. I think it's really smart. I'm not doing that in any of my slides, but you should know it's there. So we've now seen how coroutines work and how we can implement them and use them. So what? So what? Right? Is this like an interesting little quirk, tidbit that we can use? Often it seems like coroutines are a solution looking for a problem, and I thought that for a long time as well. What I'm hoping is that in this talk, the rest of this talk will give you some ideas for how we can use them. And the perspective that I want you to have is of seeing them as nanoservices. Now, I made up the term nanoservices so far as I know, but I'm sure there are plenty of other people who've talked about such things. A lot of services nowadays are described as microservice architectures, which is to say, you divide up your big system into many small systems, which are theoretically easier to write, easier to maintain, easier to integrate. So each of them has its own API. So you want to do authentication, that's a service. Database, that's a service. Updating information, that's a service. Logging, that's a service. And so each one exists across a different API. So what you can think of is a coroutine as like an in-memory nanoservice. Nanoservice, it's super tiny, it's in memory, it's going to perform a certain task for you. You don't have to worry about networking your objects or threads or process overhead because it's in memory, it's in your process, and it keeps its state around. Now you'll need to create your own protocol for communicating. I'm going to show you a basic one that I created here, but you have access to all of Python's data structures. So let me show you a few examples of what I'm talking about. First of all, MD5. So MD5 is a very popular hash function. It comes in the standard library with hashlib, and it's a little bit of a pain to use it in Python. You have to worry about bytes, and you have to worry about strings and bytes. You have to worry about whether you want to get the hex hash back, but it'll work. So what I want to do is create a coroutine that will provide an MD5 service. So how's that going to work? Well, it's going to look like this. I'm going to import hashlib. I'm going to say def MD5 gen. All right, so I'm going to define my generator. I'm going to say the output is originally none. And then I'm going to have my loop with a walrus operator, while s walrus yield output. What am I going to do? I'm going to create the new MD5. I'm going to take the string that I got from the user, turn into a bunch of bytes, and update the MD5 hashing system. And then I'm going to get a hex digest from that, put that into output, we yield, and we go around and around and around. So I can say g equals MD5 gen, and I can do send of none. That, of course, is going to prime it. It's like doing next. And then we can get the hash of this, hash of that, and then I can end it, stop the service with sending none. So this is like a little tiny service that I can run. Well, let's look at something a little bigger. Here's one to get the weather forecast. And I got this from, I believe it's called the World Weather Institute. It's associated with the United Nations. I'm sorry, I don't remember the name offhand. And the idea is that by going to this URL here, worldweather.wmo, World Meteorological Service, I think it is, .int, and JSON city, you put in a city number, many different cities are numbered there, and a JSON, and you will get back information in English in JSON format for a particular city. And that gives us a whole data structure. I can then look at weather, city, forecast day, and that'll give me a list of dictionaries. So what I can do is I can say g equals get forecast for 44, and then I can just next to get each of the forecasts for city number 44, which is somewhere near me in Israel. I think it's Tel Aviv, but I could be wrong. Yeah, but that's not coroutine. A coroutine involves us sending data to it, not calling the generator with an argument and getting things back one at a time. So let's change this to be a coroutine. So what am I going to do? I'm going to say while city ID, walrus, yield, send a city number or none. So if we give it none, it'll break out. But if we give it a city number, then we're going to yield one forecast and another and another. So g equals get forecasts. And then I'm going to say next of g, that primes it. Then I can say print g of send 44. Once again, that's going to give me the weather, the first weather forecast for Tel Aviv. And then the next weather forecast for Tel Aviv. And then the next one. And then the next one. And then the next one. Look, we're done. So we go back up to the while loop now. And it says, give me another city number or none. Well, I can give it another city number. That's pretty snazzy, huh? We're going to come back to our weather example in just a moment. But take a look at this third one. Let's say I have a database of people. Right? So I have to connect to the database. It's a PostgreSQL database. Connections take a little bit of time. They take a little bit of memory. So it'd be nice to just have the connection running already. So what I can do is I can say, here's my connection. I'm already going to connect to the database, the people database with user Reuven. That's me. And in this database, I'm going to have people. I have me and my 4 children. They like to star in my presentations, or so they told me. So what's going to happen here? Well, we are going to get a query from the user. They're going to send us a query. We'll talk about what that query is going to be like in just a moment. And so we're going to then use that to build up our SQL. And our SQL is going to have two different parts. It's going to have the main SQL, and it's going to have the arguments that we're going to use to interpolate values into there. So then I can go through each of the fields, first name, last name, birth date, and I can grab what I've got in the dictionary. That's right. They're going to be sending us a dictionary with the field names and the values that we want. It's like a super simple version of SQL in a dictionary format. And so how does that look? Well, then we're going to yield one record at a time. How does it look? We can say G equals people API. Next G, got to prime it. And I can say, hey, G send last name of Lerner. Notice I'm sending a dictionary. And now it's going to give me all of the records where the last name is equal to Lerner. And that's going to be 1. That's me. And now it says, okay, send a query or none to quit. We're back at that main while loop. So now I can send, well, I want last name equals Lerner Friedman. That's my children's names. I'm going to get 1, 2, 3 records back. And now we're back at the top of the loop. So what I have here is a super simple database query engine, but my people API generator, my coroutine, is staying in memory, and we don't need to reconnect to the database at all. It's there. And of course, I can cache things as well, as happened with these 3 results that I got back from my children. How can I tell the generator I'm completely done, that I want to finish? There is a close method. I can say g.close, and that says we're finishing up, we're stopping, and it doesn't raise a stop iteration exception at all. I should add that if afterwards you try to use it, if you say next or send, you will get a stop iteration indicating that it's done. But we also have the throw method, and the throw method allows us to raise an exception inside of the coroutine. Now, exceptions don't mean that we have errors, so this is pretty great. So let's go back to our weather example here. All right, in the weather example, I've now changed it where we're going to try to get the forecast and yield it. And remember, yield pause each time. That's where our coroutine goes to sleep. So if I raise an exception right then and there, and if I raise the different city exception, I'm going to continue. So how's this going to work? Create my generator, get forecast. I say next G, we've primed it. Send 44, great. Send 44, great. But then I throw the different city exception, and what happens? We are back to the beginning, back to the main loop, where I can send a different city. So our Nanoservice is available via a simple request and response interface, and we can use Python data structures for our input and output. This is great for network connections, database connections. We can cache the data, only get one element at a time. It's really, really nice in this way. But let's now go in the other direction. What if I want a mega service? What if I want to combine absolutely everything together? Well, so for example, what if I want to have both MD5 and weather forecasting in the same coroutine? I know, really bad idea, but stick with me for a moment. So here we have our combined generator, where at the top it's going to ask us to send either 1 for weather or 2 for MD5 or none to exit. Brilliant software design, I promise you. So if I say s equals 1, so if the person wants weather, then we're going to do the weather stuff. And if they want 2, then we'll do the MD5 stuff, and this will actually work. Next to G send 1, G send 44, different city exception, very good. We can then send none, go back to the top level. It's like having an operator, right? Press 0 to go to the top. And then we're going to be able to say, I want to do MD5, hello, exclamation point. All this stuff works just fine. And as I like to say, unfortunately, this works. And I say it's unfortunate because this code is super ugly and super convoluted. If it were a function, we would break it down into smaller pieces. Can we do that with our generator? Well, let's try. I'm going to have a combined generator here. And I'm going to say, if S is 1, run the city generator. If S is 2, run the MD5 generator. This should work, right? No. What's going to happen is every time that I run next to G, it's just going to say send 1 for weather, 2 for MD5, none to exit. It doesn't matter what I send. It's not going to work. And the reason is that our combined generator is just a regular function. It doesn't have a yield in it. We need to yield something. If there's no yield, it's not considered a generator and thus can't be a coroutine. Maybe we could just iterate over the items the generator returns. That seems really tempting, but it's not enough. Because think of it. We are sending to the outside generator, the combined generator. It's then going to have to send to the internal one. What about getting results back? And what about if we run throw or if we run close? This is where yield from comes to the rescue. So many people think that yield from is just another way of saying for each item in this generator, yield what it gave me. But no, it connects the outer part and the inner part. It connects the sender with the inner generator, with the sub-generator. So now if I say, if S equals 1, yield from city generator. If S equals 2, yield from MD5 generator. And Yield 5 now has provided us with bidirectional communication with a coroutine from the outside. So I send to the outer, goes to the inner. Data from the inner goes to the outer. Exceptions work. The inner one can even be closed with close. So Yield from is made for coroutines. And we can see here how it works just great. G equals I combined generator. Next, send, right? And it just works. We can even throw it our exception here. So where does async IO have to do with this? Early versions of async IO used generator functions and used coroutines in the sense that we've talked about them now. And they're perfect for cooperative multitasking, which is what async IO basically does. We have a whole bunch of them on our loop, on our event loop. We can start and stop it. Send. Go back to the beginning, send, and inside each of them yields at a certain point. But async IO has moved away from using generators. It now uses async def and await. And those are slightly different ideas and certainly different implementations. So don't think that coroutines in async IO and coroutines that I described to you here are the same thing. They are related. They're cousins, but they're no longer the same, and they're definitely not interchangeable. So should you use coroutines? You know what? They can be very useful. You have this speedy in-memory API. We can work with large data one chunk at a time. We can divide them into smaller pieces and use yield from with subgenerators. But, and these are cautions you should think about before doing it, they're not so well understood by people, and it might be weird to use send in this way, so you might want to use an API to wrap that. And when things go wrong, they can be really hard to debug. I hope that this was a good introduction to generators, coroutines, and yield from. I would be happy to entertain questions or comments. I would love to hear from you online as well, whether it's Twitter, my YouTube channel, or as I mentioned earlier, my Better Developers mailing list. Thank you so much for having the opportunity to speak to you today, and I look forward to answering your questions and being in touch after this as well.